Hello friends, continuing with series of special diodes in electronic devices. Today we come to two other photonic devices, LED and laser diodes. Today's topic is LED and laser diodes. We take up one by one. First we take up LED. LED stands for light emitting diode. L for light, E for emitting, D for diode. Light emitting diode. In short form, we call it as LED. First, introduction. LED converts electrical energy into light energy. I repeat, LED converts electrical energy into light energy. Second, construction of LED. As I earlier told you that all diodes are PN junctions. So LED is also a PN junction with a transparent cover for the light emitted to come out. I repeat, LED is a PN junction with a transparent cover for the light emitted to come out. Now third, circuit symbol. Circuit symbol is as shown here. A diode covered with a transparent cases which is shown in the form of circle and two photons which are being emitted out. Wherever you see such diagram, immediately you assume that it is an LED. Fourth, operating bias. LED operates under forward bias condition. Look at this diagram. Here N-type material is connected to negative terminal of battery and P-type material is connected to positive terminal of battery. It means this diode is forward biased diode. Fifth, working principle. Working principle of light emitting diode is spontaneous emission, and it is the process by virtue of which a photon of energy h nu is emitted when an electron jumps all of a sudden from higher energy states to lower energy states. I repeat, the principle of LED is spontaneous emission and is the process by virtue of which a photon of energy h nu is emitted when an electron jumps all of a sudden from higher energy state to lower energy state. Look at this diagram. In this diagram, an electron has shifted from valence band to conduction band, leaving behind a hole in the valence band. And when this electron falls back to valence band, neutralizing the hole in valence band, then it emits a photon of energy h nu 1, which is spontaneously emitted photon. Similarly, look at this diagram. In this diagram also, an electron is shifted from valence band to conduction band, leaving behind a hole in the valence band. And when this electron falls back to acceptor level, again it emits a photon of energy h nu 2. Okay. So this is how this is spontaneous emission. All of a sudden it happens. An electron falls back to valence band. So all of a sudden the electron which is in conduction band falls to valence band and emits a photon of energy. So this process is known as spontaneous emission. All of a sudden means spontaneous. So these are called as radiative transitions. Such type of transitions are called as radiative transitions. In this diagram, AL means acceptor level, DL means donor level. Now we try to understand about non-radiative transitions. First we develop the concept of radiative transitions. Jumping of electrons from conduction band to valence band, conduction band to acceptor level, donor level to valence band or donor level to acceptor level are radiative transitions. Now, non-radiative transitions. Jumping of electrons from conduction band to donor level are non-radiative transitions. So this is how we develop the concept of radiative transitions and non-radiative transitions. These are radiative transitions and these are non-radiative transitions. From diagram you can make it clear which are radiative transitions and which are non-radiative transitions. Okay. And now function. Under the impact of forward bias, electrons shift to higher energy state, that is conduction band, and when all of a sudden fall back to lower energy state, emit a photon of energy which is in visible region of light as shown in diagrams. Okay. You can look into the diagram to understand this process of spontaneous emission under forward bias conditions. Now, factors affecting wavelength of light emitted. A. Wavelength of light emitted depends upon energy gap, Eg equal to Hc by lambda between conduction band and valence band. And B. Intensity of light emitted depends upon forward bias applied, because more the bias, more will be the number of electrons shifting to excited states. I repeat, A. Wavelength of light emitted depends upon energy gap, Eg equal to Hc by lambda between conduction band and valence band. And also intensity of light emitted depends upon forward bias applied, because more the bias, more will be the number of electrons shifting to excited states. So these are the two factors which affect the wavelength and intensity of light emitted. These are, first is energy gap, second is forward bias. Energy gap affects the wavelength and forward bias affects the number of electrons shifting to excited states. Okay, because more is the forward bias, more is the current flowing through the diode, and more are the number of electrons which are being shifted to conduction band. Okay. Sixth, materials used for making LED. Now, wavelength of visible spectrum range from 7000 angstrom red to 4000 angstrom violet, and energy ranges from 1.8 electron volt for red and 2.8 electron volt for violet. Since wavelength of light emitted depends upon energy gap between valence band and conduction band, therefore those materials are preferred whose energy gap lies between 1.8 electron volt to 2.8 electron volt. It is therefore p-doped gallium arsenide, that is gallium arsenic 1 minus X, Px, or gallium phosphide are preferred materials. The germanium with energy gap 0.78 electron volt and silicon with energy gap 1.21 electron volt can't be used because of lesser energy gap. because energy gap required should be 1.8 electron volt to 2.8 electron volt for the light to become visible. Uses: LED is used as display device. Also, it is used as an optical source for optical communication. Assignment 14 continued. Question number 46. What is light emitting diode LED? Mention two important advantages of LEDs over conventional lamps. Question number 47. State the factors which control number 1 wavelength of light emitted and number 2 intensity of light emitted by an LED. Okay. Second, laser diode. Now we talk of laser diode. Introduction. Acronyms are L stands for light, A for amplification, S for stimulated, E for emission, and R for radiation. I repeat, L stands for light, A for amplification, S for stimulated, E for emission, and R for radiation. All these 5 letters L, A, S, E, R forms the word laser. Now what is laser diode? Laser diode converts electrical energy into light energy by spontaneous emission like in LED, and then amplifies the light so emitted by stimulation due to spontaneously emitted photon. I repeat, laser diode converts electrical energy into light energy by spontaneous emission like in LED, and then amplifies the light so emitted by stimulation due to spontaneously emitted photon. Second, construction. Laser diode is a PN junction whose sides have high quality polish such that it acts as a partially reflecting surface and also enables back reflection process. So this is partially reflecting surface and this is back reflecting surface. Third, operating bias. It operates under forward bias conditions. Fourth, working principle. Working principle is stimulated emission. What is stimulated emission? Let us see. It is the process by virtue of which a spontaneously emitted photon of energy h nu, which is equal to E3 minus E1, enters into the system of population inversion and stimulate the electrons to fall to ground state E1, emitting a photon of energy E2 minus E1, which is equal to h nu. I repeat, the process by virtue of which a spontaneously emitted photon of energy h nu, which is equal to E3 minus E1, enters into the system of population inversion and stimulate the electrons to fall to ground state E1, emitting a photon of energy E2 minus E1 equal to h nu. So here look at this diagram. So this is a spontaneously emitted photon which enters population inversion system and stimulates the electron to fall, releasing another photon of energy. So this is photon of energy which is due to spontaneous emission, and this is a photon of energy which is due to stimulated emission. Okay, and the two are in phase. This is how it constitutes the principle of working of laser diode. Fifth, Population inversion. Now let us try to understand population inversion. When the rate at which electrons go from ground state to excited state is more than the rate at which they fall to ground state, then state of population inversion is reached. That is, number of electrons in excited state are more than the electrons in ground state. Now look at this diagram. So here you see this is excited state where electrons are more in number than the electrons in ground state. So this is a population inversion state. Now sixth, working. Step by step we'll take up working. First step, spontaneous emission. How spontaneous emission takes place? Let us discuss. Under forward bias condition, current flow through the junction. Initially, at low current, as in LED, there is spontaneous emission in all directions. Look at this diagram. So this is spontaneous emission in all directions. Now second step, population inversion. As the bias is increased, a threshold current is reached at which stimulated emission occur. Due to DC bias, electrons go to higher energy states, causing population inversion. So at threshold current, the electrons will shift to excited states, causing population inversion. The third step, stimulated emission. How stimulated emission takes place? Let us see. When a spontaneously emitted photon of energy h nu equal to Eg enters the device while it is still in excited state, that is population inversion state, the system immediately gets stimulated to make its transition to ground state and give an additional photon of energy h nu, which is in phase with the incident photon. I repeat, when a spontaneously emitted photon of energy h nu equal to Eg enters the device while it is still in excited state, that is population inversion state, the system immediately gets stimulated to make its transition to ground state and give an additional photon of energy h nu, which is in phase with incident photon. So this is incident photon, this is stimulated emitted photon. Now fourth, amplification by multiple reflections. Further, amplification of light takes place due to multiple reflections in cavity in a plane perpendicular to depletion layer due to plane polished surfaces. A highly directional, coherent and intense beam of light is emitted, which is a low power laser. I repeat, further amplification of light takes place due to multiple reflections in cavity in a plane perpendicular to depletion layer due to plane polished surfaces. A highly directional, coherent and intense beam of light is emitted, which is a low power laser. Now seventh point, uses. Laser diode is used as an optical source in optical communication system. I repeat, the uses. Laser diode is used as an optical source in optical communication system. Assignment 14 continued. Question number 48. What do acronym laser and LED stand for? Name the factors which determine frequency and intensity of light emitted by an LED. Thank you so much. Here we finish with diodes. Next time we'll take up another electronic device which is called as transistor. Till then, Goodbye and good luck to you.